All right, it's recording there. And I'll record with my alternate method. All right, let's continue now. Now, let's say that we have this molecule right here. Let's do N2. This is nitrogen molecule. This is the molecule that you're breathing right now. That is 70% of the air that you're breathing is nitrogen molecule. All right, so let's see what we can do here. So same things apply, except now we only have one atom type that we have, but there are two of them. Easy thing to miss here. There are two of them. And so there are 2 times what? 2 times, and we look at our periodic table and we go 1, 2, 3, 4, 5, 2 times 5. It gives me 10 electrons total for the whole thing, for the whole molecule. Now, since there's 2 atoms, it doesn't matter which one we call the center atom because they're really the same thing. And so I'm just going to park them next to each other. So I have nitrogen, nitrogen. There we go. Nitrogen, nitrogen. Now, what do? We go ahead and make a bond. That's all we can do, right? We start in the middle. We're in the middle. We made a bond. So it's -2. We have 8 left over. All right, how much room do we have for each one? Room would be 2 times 6 equals 12, right? But look, how many do we have? We have 8. All right, we don't have 12. So what we need to do is we need to split 4 each. That's what we need to do. So I'm going to split 4 each. And so I'm going to say 2, 4. Remember, we keep pairs. Electrons do not like to be not paired up. All right? They want to stay pairs. So we keep them paired. And so let's go ahead and put 2 over here as well. Okay, so we put down 8 altogether. We have none left over. Remember what I said. Whatever you do, don't put down any more than what you have. You had 8 electrons, that's what you had. You had room for 12, which is 6 on each, but you didn't have 12. You only had 8. So what do you have to do? You put 4 on each one. Nature wants symmetry. Symmetry means same on both sides. So that's why I put 4 on each one. You could have put 6 on one and 2 on the other. Okay, been all right. But nature doesn't like that sort of thing. All right, so now what do? Well, if I look at these nitrogens, are they happy? And the answer is no, they're not. They both have 6 electrons on them that are including the shared electron. So what can we do? So what I'm going to do is I'm going to go ahead and just drop this pair in. And if I do that, I'm going to end up like this. Okay? And it's still not happy. And so having done that, remember what I said about symmetry. I did it to the right. Let's do it to the left. And so the left one, I'm going to go ahead and drop this pair in. And if I do that, now what do I have? I have 3 pairs dropped into the middle. Y'all see that? Just dropped them right in. All right. So the first one, here was the first shift. There's the second shift. And keep in mind, when you're moving these electrons, they never leave the atom that they started out on. All I did was pivot them in from being non-bonding into bonding. Now what do we have? Well, now let's check. And we see that we have, you see that? 2, 4, 6, 8. Happy. You see that? 2, 4, 6, 8. Happy. Whole thing's happy. And so if we were to draw this, we would say 3 pairs, 3 lines. There's those 2 extras that are on the out. Those are non-bonding. And so we would say this is a triple bond. It's a triple bond in between. Guess how much stronger a triple bond is than a single bond? It's times 3 stronger. One of the rare things that are going to make sense in chemistry this entire semester, believe it or not, a double bond is just about twice as strong as a single bond, and a triple bond is, guess what? It's actually about 3 times stronger than a single bond. Nothing else will make sense, but this will. That's the way it goes. But yeah, really, literally, it comes down to that. How much stronger are they? Literally, it's 3. And oh, by the way, can there be, and you should be, as a sciencey sort of person, we've had a single bond, we've had a double bond, we've had a triple bond, and you should be asking yourself what? I wonder, can you have a quadruple bond? What do you think? And the answer is no. No quad bonds. Just singles, doubles, and triples. No quadruples. And the reason is because of the way they fit. And we're going to cover this next chapter. There's no quad bonds. The reason is because the first bond goes this way. And believe it or not, the second bond goes this way. This is bond number 2. And then the third bond goes this, the third bond goes this way. That's supposed to be 3-dimensional. Okay, so you got 1 going down the middle, and then you got 2 that are kind of like facing each other edgewise. And there's no more room. There's no more room because you go 90, 90, 90, and that's it. That's all you can fit. So because we live in 3-dimensional space is the reason why you can't have no quad bonds, no quad bonds. Okay, because there's just no more room. Y'all see that? The one goes down the middle. By the way, looking ahead, the one that goes down the middle is called a sigma bond, and these guys are called pi bonds. All right, sigmas and pi's. Okay, that's what they have. That's the next chapter, but it's coming up. All right. So you can have a single bond, you can have a double bond, and you can have a triple bond, but there are no quadruple bonds. All right, it's not like figure skating where you can have a single, double, and a triple. You can have a quad. There are no quads in chemistry. All right, there are no quads. Okay. So there you go. So nitrogen molecule has a triple bond. Now, let's say that we had this guy right here. All right, SF6, which is a real molecule. It's a gas. It's a non-toxic gas. And it is called, well, let's see, it's a covalent molecule, so we name it with prefixes, and we call this sulfur for the first part. What do we call this? We call this 6 is hexa, and of course this is fluorines, so we call this fluoride, sulfur hexafluoride. All right, so let's draw the molecule for this. Now, we see sulfur. We look across our periodic table and we go 1, 2, 3, 4, 5, 6. It has 6 valence electrons. And we see fluorine. Well, there's 6 of them. Okay, let's not forget there are 6 here. So what do we have here? We have 6 there. And we look across the periodic table and we go 1, 2, 3, 4, 5, 6, 7. we see it's the seventh one across. What's 6 times 7? Let's see, that would be 42. 6 times 7, 42? Yes, it is. And we add them up, and we have 48 electrons. So far, so good, right? All right, now, we'll start with the sulfur. We'll put this in the center. And we have the fluorine. Here's a fluorine. There's a fluorine. North, east, south, west. Uh-oh, we're running out of room here. Remember, how many do we have? We have 6 fluorines. So I'm just going to go ahead and park the extra fluorines up over here on like that, okay? We got to put them somewhere, okay? Now, let's go ahead and make a bond. We're going to make bonds. So how many bonds are we going to make? Well, here's a bond there. There's a bond there. Oh, wait, let's not forget. We got to bond these guys on too. Those ones parked off on the angles. How many did we just put down? Well, let's see. 6 times 2, that's 12. We just did 12 electrons. We subtract off. We have 36 left over. Right? And 12 from 48, 36. Okay, how much more room do we have? Well, let's see. I got 6 fluorines. How much room? I have 6 fluorines times 6 open. What I mean by open is how many spots do I have available. That's 36. I got 36, so I can put down all 36. So let's go ahead and put down all 36. We'll have 0 left over. So we do that. So here's 2, 4, 6, 2, 4, 6. Now let's not forget about this guy down here too. 2, 4, 6. Now I'm clustering them in so you can tell that, you know, they're on that fluorine. Okay, 2, 4, 6, 2, 4, 6. Let's not forget this one up in the corner. 2, 4, 6. And I put 6 on each fluorine. Well, there's 6 of them, so that's 36. I mean, there are 6. They have to have electrons. I know it's getting to be a busy party. All right, but they're there. All right, let's check for happy atoms. How about those fluorines? Yeah, they all have 6. So the fluorines are all happy. Now, how about the sulfur, though? The sulfur has how many? Has what? Has 2, 4, 6. Well, there's 6 times. It has 12 electrons, doesn't it? It has 12, doesn't it? Look at that. It does have 12. Let's see. 2, 4, 6, 8. Wait a minute. Hold on. I'm missing. Oh, there it is over here. There it is. Let's put that guy in there. It does have 2, 4, 6, 8, 10, 12. It does have 12 electrons, right? It's okay. It's okay. Put a little happy face so you know for sure it really is okay. It is okay. This is what's called hypervalent. This is hypervalent. Now, remember what I said about the octet rule? Remember that? And I said octet rule, and I said, oh, well, atoms want to gain, lose, or share electrons that have full valence shells. And I said, oh, by the way, it's not necessarily 8, but take a look at the periodic table and you see that, you know, they all want to be just like the noble gases with 8 valence electrons, right? Well, I lied to you. As usual in chemistry, there's all sorts of exceptions that are important, and this happens all the time. So the octet rule is not much of a rule at all. It's not much of a rule at all. But if you stick to like organic chemistry, it generally works. But this happens all the time. This is a real molecule. It has 6 fluorines attached to it. And okay, so the generally accepted first approximation is we are expanding out the D's. Generally speaking, that is the first explanation. Is folks will tell you, oh yeah, it's the D levels. Remember when I said they like the exceptions for copper and for chromium, we said the S got promoted to the D's, and the half-filled shells versus the full-filled shells, and that's what they say. Okay, they say it's a D's expanding out. This is why we have the extras, and this is where if you decide to become more in depth with this sort of thing, you'll realize that if you do some computational stuff, in other words, with big computers, with lots of deep thinking and things like that, it's not really the expanded out D levels. The D's do contribute, but they don't contribute as much as you would think. So what is the true explanation? Because you know what? I'm a sciencey sort of person, and I don't like, these little statements like this unless they're true. So what's really going on? I'll tell you what's really going on. Here's what's really going on. All right. I'm going to share the secret with you, and it's not even a textbook. I don't think they even mention it in the textbook. Sulfur, big or small? You look at the periodic table, and it's down further in the periodic table, right? Sulfur's a relatively big atom. Remember the rules for, the size of atoms? As you go left to right, they get smaller. Top to bottom as they get bigger. Sulfur's a relatively big atom. Fluorine, big or small? It's relatively small. It's in the upper right-hand corner, and remember what it says, left to right, smaller, right? And as we go higher up in the periodic table, they're smaller. Fluorine is about as small as you can get next to helium. Fluorines are small. Fluorines are small, and they're hanging off like little ticks, aren't they? Like little tick, like little atom ticks. All right, they're hanging off. Fluorines are small. These guys are small. This guy is big. All right. So what do you think? Do you think a bunch of small things can fit around a big thing? Yeah, that's what it is. That's what it comes down to, is you can just simply fit more around it. It's actually a physical fitting kind of thing. The reason why you don't see this with things like carbon with hydrogen is because carbon's already small, hydrogens are small, so you just can't fit them. You just can't fit a bunch of hydrogens around a carbon because you just run out of room. Carbon's already small, but if you take something like a sulfur, you can fit a bunch of fluorines around it. If you take something that's even more humongously humongous, like iodine, iodine can actually fit a bunch of fluorines around it. Iodine is humongous, and you can stick a bunch of little fluorines all the way around it. You can do this, even though 1, 2, 3, 4, 5, 6. You can fit them for no other reason than that they're big and small. So if you do see, where you see a statement such as the reason why this happens is because because the D levels are mixing with the S's and the P's, and that is partially true. But if you actually put it in deep thinking with very big computers and lots of computational time, that is a contribution, but it's not really the most important contribution. Really, the most important contributions is just sheer size. It comes down to size. All right, that's what it comes down to. All right, so we can do things. We can do some interesting things with these expanded octets. So we can take a compound that exists, such as xenon tetrafluoride, which is an actual compound. It's one of the few halogen compounds that you can make, and it's stable. So what would we expect? So we would say xenon, oh, wait a minute, that's a noble gas, isn't it? And we don't expect noble gases to make compounds, do we? But that's one of the ones that they can make. Xenon, it's a colorless crystal. If you bang on it with a hammer, it explodes. All right, so let's make this one. Let's see what it looks like. So we say xenon. Well, that's got 8 valence electrons, right? And fluorine, well, there's 4 of them, and there's 7 apiece. So that would be what? 28. And now we have 36 altogether. And just say xenon in the middle, fluorine, 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 fluorine. Go ahead and make some bonds. You can do this quickly. And once you get the habit of doing this, it's actually relatively quick. So it made 8, let's see, 8, that would leave what? 20, what is that? 20, 28? 28, yeah. 28 left over. I have room for 6 on each. So 6 times 4 is 24. So I have 4 left over. Oh, this is getting even more interesting, isn't it? I have 4 left over. And so let's go ahead and put down those 24 electrons. So we have 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, and 6. That's 24 with 4 left over. What do we do with those leftover electrons? We put them back on the center. Remember that when we did the nitrogen trifluoride? Leftover electrons go back onto the center as what? Lone pairs, and we circle them. Xenon tetrafluoride has 2 lone pairs. That's where those 4 go. They go in as lone pairs. All right, now the pair means 2. So if you have 4 electrons, that's 2 pairs. 2 pair. All right, there's xenon tetrafluoride. There it is. Okay. How about let's do an even more exciting one. Let's try another one. Okay, so let's try let's see. How about let's make an iodine compound. Let's go iodine. That would be 7. And let's go with 3, 4. Oh, yeah, let's do iodine. Let's see, that would be 5 times 7 would be 35. Iodine. Ooh, here's a fun molecule. Here we go. Fun molecule. Iodine trifluoride ion. Iodine trifluoride ion. Now, how would we handle this? We would say, well, first off, we got to count up valence electrons, right? So, got to be able to count. So, we have the iodine, we have the fluorine. Iodine has 7, and there's 1 of them. Just so I can stay the same, we'll say 1 times 7 is 7, and there's 4 fluorines there. Times 7 is 28. Okay, but I want to draw your attention here. There's more to this. You have the iodine with 7. You have the fluorine with 7 apiece, right? Well, what about this? That means 1 extra electron, doesn't it? So we have to put that in there as 1. So now we have 36 electrons. Okay? And I'm going to put here, easy to leave off. Because what does it mean to be minus? It means you have an extra electron. What does it mean to be plus? It means you're missing an electron, so you'd actually have to subtract 1 off. And so now we're back to an even number of electrons. If you see an odd, something's wrong. All right, that's a pro tip. Now, you can have odd electrons. They're called what are called radicals. and they're very reactive, and they do exist. But for our purposes, for stable molecules, generally you want an even number of electrons, generally. All right. And so if we do that, now we can go ahead and say, iodine in the middle. You got your fluorines. Once again, here we go. Go ahead and make those bonds. Let's see, that's 8, right? And let's see, that would make 28 left over. Yeah? And so now let's go ahead and fill out these fluorines. We're going to put 6 on each one. Okay, I put 6 on each one. They're kind of smudged, but forgive me, I'm using a graphical tablet. And so let's see, 6 times 4 is 24. Got 4 left over. So now we have 2 lone pairs we can put down. There's a pair. There's a pair. Let's circle them so they emphasize that they take up space. Minus 4, 0, we're done. And so if you were to draw this molecule, it would actually look like this. Let's see, that would be lone pairs. Yep, so it would actually look like this. Lone pair, and we have these guys going up, these guys going up, and these guys on the equator, and there we go. That's what it would look like. Okay, and I left off the extra non-bonding pairs because we're going to get to a point where we really don't care about them, but they're there. Okay, just for completeness, let's go ahead and put them on there. So if we did that, they would be like this. They would be there. Okay, they are there. I just left them off. Okay. All right. So these are actually quite exciting molecules, and they're quite real, and that's how you would do them. So the thing that I wanted to emphasize here, though, is this part right here. Look, if you have a minus, if you have a charge up there, you have to account for it. Oh, how about let's do the positive version of IF4. Let's do the positive version. Let's do IF4 plus. Let's do IF4 plus. So now we have, instead of the anion for iodine trifluoride, let's do the cation for iodine trifluoride. And so we would do the same thing. We say I and F, and that would be 7, and this would be 4 times 7, which is 28. Well, what about this guy right here? I'm going to have to subtract off 1 because what does this mean? It means we're missing 1 electron, doesn't it? That's what it means to be put. This is what I mean. Don't ever stop trying to say, well, what does this really mean? When you're positive, what does it really mean? It means you're missing an electron. That's what it means to be positive. And so if we subtract this guy off, now we have 34 electrons, don't we? Did I do that right? Yeah? So 1 from 7 is 6. 6 plus 28 is 34. So I have 34 electrons. So now I have an even number of electrons, which means I'm on to something. And so I can go ahead and do this now. So I have I, F, 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 F. Did I do that right? Let me see. 28, 32. What did I do on that previous page? It should have been 36 on the previous page, wasn't it? Yeah, it was. All right. 35, 34, 36, 32. What did I do on that previous? Anyway. All right, so let's see. Let's see if this works here. So and we subtract off 8, which would be 26 electrons. We have room for 24, which means we have 2 extra. All right, there's 24, 2 extra. So in this case, instead of 1 lone pair, we now have, 2 lone pairs. Now we have 1 lone pair. So our previous page, we should have had 36 electrons. And there it is. And so we had 36 on the previous one. See that? We had 2 lone pairs with the minus. And with our new version here, where we have the positive version, now we have 34 electrons. Now we have 1 lone pair. 2 totally different molecules. 2 totally, entirely different molecules. All right? One's the cation, one's the anion. One has 1 lone pair, one has 2 lone pairs. Matter of fact, when we get into the geometries, we will see that they're totally different shapes too. And they'll react totally differently between the ion F4 minus and ion F4 plus, assuming that they even exist at all. I'm sure we can make them exist at least for a little while before they fall apart. Okay? All right. So there you go. So that's how you do these Lewis structures. Okay? So if you end up with a whole bunch of extra electrons, just keeping a whole bunch of extra bonds, just keep in mind it's okay. It's okay if you violate the octet rule for the fluffier molecules, so to speak. All right, those are fluffy ones. All right, any questions on this? All right, so we've got one more thing to cover. Actually, we got 2 more things to cover. So let me cover one more thing. We're going to do resonance structures, and then we'll call it a day. All right. All right. Now, let me make a thing here. Oops, there it goes. So let's say we have this molecule right here. Okay, this is after we've drawn it out. We've done our Lewis dot structure. And this is what we ended up with, okay? Just take my word for this. This is sulfur trioxide. All right, it's got a double bonded oxygen, and it's got 2 single bonded oxygens. All right, now, if you were to look at this experimentally, you would expect the double bonded oxygen to be shorter than the single bonded oxygen. You would expect, okay? You would expect, because the double bond is stronger than the single bond, it will pull the double bond shorter and closer together. Just because it's stronger, it's going to pull on it harder, okay? More on that later as far as the absolute lengths, but keep this in mind. Single bonded, double bonded is twice as strong as a single bond. Triple bonds 3 times as strong as a single bond. Single bonds are longer than double bonds. Double bonds are longer than triple bonds because of the strength. All right, now, you would expect this, but experimentally, they're the same. They have the same length, which means they're the same bond experimentally. So we have to explain this. And the first explanation that we come up with is this whole idea of resonance structures. Okay, the whole idea of resonance structures. And the idea of resonance is that we're going to say that the bond actually walks around. That it does this, that it's an equilibrium. In other words, all 3 structures exist at the same time, is what we're going to say. The atoms are not moving, okay? The atoms are staying put. But the double bond exists in all 3 forms simultaneously. This is the same molecule, except we have rotated 120 degrees in a sense. So there's a symmetry argument going on here. Okay? It's the same molecule. All three of these are the same molecule. And we're saying it's kind of like watching a movie. You know, a movie is one frame at a time, but the frames happen so fast that you can't tell that it's one picture at a time. So it looks like it has the illusion of motion. So we're saying all three of these come together. And so what we're going to say is that the double bond character is smeared across all three bonds at the same time. So now we have three equivalent bonds. And since there are three equivalent bonds, they're not quite a single bond, they're not quite a double bond, they're somewhere in between. And so they're sharing that character among all three bonds. And so this is a hybridized structure, but these are the resonance structures. So there's three of them. There are three equivalent resonance structures. All right, and this is for SO3. Now, what do we have to have for a resonance? You have to have a double bond next to a single. Double next to a single is what you have to have. They have to be physically next to each other. The double bond has to be next to a single bond. And it has to be the same pair. See that? It has to be the same pair. It has to be a single and double next to each other, but it has to be the same two pair of atoms. Now, in this case, it's a sulfur next to an oxygen, and there's also a sulfur next to an oxygen, and it's a double bond next to a single bond. So you have three opportunities. You can go all the way around, all three equivalencies. So let me show you where it would not happen necessarily. Let's take one of those oxygens, and let's replace it with a sulfur. All right, so we have a double bond next to a single bond. We have the same pair here, but we do not have the same pair there. And so the resonance structures that we can draw is just two of them. And so it would be, and that's it. Okay, in other words, this from here to here is not going to happen. Okay, so it is going to, whoops, I meant to do the other color. So let's see, it is going to go between these two. Okay, it is going to go between those two. All right, so those two rules have to apply. One, it has to be a single next to double. And two, it has to be the same kind of pair. All right. And the way I like to think about it is I like to think about this as you walk the double bond. That's how I like to think about it. You walk it around. So when you look at the previous one over here, when you see this, I walked the double bond around. I walked it from here to there, from here to there, from here to there. See, I'm walking it around. That's what I mean by walking the double bond. And so if you have something like ozone, which is another classic example, ozone is O3, and its structure looks like this. It's a bent molecule, but it can go in between these two structures right here. That's what happens with ozone. It just goes in between the two. All right. And another one, which is where this whole thing got started, is something called benzene. And it's this six-membered ring. It's got alternating double bonds. and it walks between two structures. This double bond goes here, that double bond goes there, that double bond goes there. And so it ends up like that. Do you see how it did that? It went from here to there. Okay. And so there's only two resonances here. And there's only two over here as well. All right. If you moved one, you got to move the other. Because if you moved only one, you would have these guys next to each other. See that? If it's going to be alternated, it needs to stay alternating. Okay, that's the reason why there's only two. Because you may look at this and say, but wait, you know, there's 3 double bonds. Maybe I have 6 possible structures or whatever. But, you know, if you move one, you got to move them all. All right, so you got that. So you have resonance structures. Now, what's an easy way to tell, and I'll leave you with this, how can we tell if I have SO2, SO3, PO4? How many? How many resonance structures? Now, this is not a rule. This is not a rule as in a physical rule, but this is quizzes, homeworks, and tests. How do you tell? Quizzes, homeworks, and tests. How do you tell? Well, look, this is how you tell. You look at this number right here compared to these guys. This would have 2, this would have 3, this would have 4. This would go in between these two just like this. See that? This would be the same deal. This goes between what we just did, just like that. You see that? And you got 3 of them where it walks around. See? 3 ways it can walk around. 1 way it can walk around here, so you got 2. And PO4 is the same way. It can walk around 4 times. See that? But without actually drawing out the structure, what would be your first guess? If you were to guess, if I was just to look at the formula and make a guess, that's what I would do. I would say SO2, yeah, it should have 2 resonance structures without actually having to sketch it out. Strictly speaking, you should sketch it out. But if you're in a hurry, you can always say, well, you know what? It's got 2 oxygens. I'm going to guess it has 2 resonance structures. And you would be right. The phosphate ion, which is what this guy is right here, how many resonance structures would it have? Well, I'm going to guess that it has 4, and it does. It has 4. But that's only because we're saying that we have 4. This is my justification. We have 4 equivalencies here. You see that? That's how I can justify saying that 4, it will have 4. That's for my first guess. Same thing here. If I have 3 oxygens, I'm going to guess that I have 3 equivalencies. Same thing here. If I'm going to guess there's 2, I'm going to say there's 2 equivalencies here. That's what I'm doing. Okay? All right, y'all. I am out of time. Let me turn off the recorder because I don't want to